Namaste everyone, welcome back to our YouTube channel. We have started new series for NCERT class 10 mathematics, and this is our second lecture for first chapter. In this chapter we'll be seeing Euclids Division, algorithm or lemma, some examples based on this theorem, and exercise 1.1. So before starting with this lecture, let us discuss few points regarding this YouTube channel. We will be covering every chapter for class 10 NCERT syllabus, and already we have completed one lecture. Please do subscribe our channel, and if you have any suggestions which help us to deliver more quality lectures, then please do comment on those videos. So this will be our second lecture. The first point we will be discussing is Euclids Division lemma or Euclids Division theorem. So before commencing with this lecture, let us discuss few concepts regarding division. So what is dividend, divisor, quotient and remainder? These concepts has to be understand. You need to understand these concepts before studying the Euclid's division lemma, because these concepts will be used there. So let us first discuss this problem. 455 divided by 42. So which will be the number which can be, all of you know that 35 is the remainder. After dividing 455 by 42, you will get answer as 10 and remainder as 35, because 42 tens are 420, so 455 minus 420 will be 35. So what will be the dividend in this example? It will be 455. What is the dividend? 455 is called as dividend. What is the divisor? The number by which we divide the given number is called as divisor. So what will be the divisor? It will be 42. So quotient. After dividing the given number by the divisor, we get answer as 10. So quotient will be 10. And remainder is 35. So all of you know the concept of remainder. Only thing you have to remember is what is dividend. The number to which we divide is called as dividend. It is 455. The number by which we divide is called as divisor. What is the divisor here? 42. So there is one generalized formula to represent this relation. Dividend equal to divisor into quotient plus remainder. Understand this. Dividend means the given number, divisor by which we divide the given number, quotient will be our answer, remainder will be 35. So dividend, that is given number, equal to divisor, that is 42, into quotient 10, quotient is 10, plus remainder is 35. So 42 into 10 plus 35 equal to 455. This relationship is represented in this generalized formula. Dividend equal to divisor into quotient plus remainder. So what is dividend here? It is 455. So again understand that dividend equal to 455, divisor is 42, quotient is 10, remainder is 35. Okay, dividend equal to 455 and divisor will be 42. What is the divisor here? 42, the number by which we divide. 42. Quotient will be 10 and remainder is 35. So 455 equal to 42 into 10 plus 35. This is the generalized formula. You have to remember this one. Now let us understand few examples based on this particular theorem. This theorem is very important. It will help us to find the HCF. We will be seeing that in our subsequent lectures. So first understand what is the theorem. What is the theorem here? Euclids Division Lemma or Euclids Division Theorem. How will you define it? Given the positive integers a and b, there exist unique integers q and r satisfying this relation a equal to bq plus r, where value of r is between 0 and b. 0 is less than equal to r is less than b. So this is the generalized Euclid's division lemma. What is the significance of this theorem? By using this theorem, don't bother about these relationships. We will be seeing these terms a, b, q and r. Just focus on the theorem, how we will be using this. Euclid's division algorithm is a technique to compute the HCF of two given positive integers. Okay, we can find the HCF of any given two positive integers using Euclid's division lemma. Before this, we have seen the prime factorization method. By that method, we can find the LCM and HCF of any two numbers. But this Euclid's division theorem will help you to find HCF within few steps. If numbers are large, then it will help you to calculate the answer within few steps. We don't have to factorize those large numbers. Okay, so what is the main use of this theorem? We can find the HCF. So what is the HCF? Just recall the concept of HCF. HCF of any two positive integers a and b is the largest positive integer d that divides both a and b. So we have to find the largest number which can divide the given two numbers. That is called as HCF. So we have seen the prime factorization method. What is the prime factorization method? We have to factorize the given two numbers. So in this example, we have two numbers as 455 and 42. So let us first calculate the HCF by using prime factorization method. So what is prime factors of 42? 2 into 3 into 7. You will get the answer as 42. We have seen how to find these prime factors. Please refer to our first lecture. You will understand how to obtain these prime factors. Now let us look into the 455. What are the prime factors of 455? 5 into 7 into 13. So what is the definition of HCF? Smallest power of each common factor. So common factor here in these two prime factors is 7, and its smallest power is 1. So 7 raised to 1 will be the HCF. So now let us calculate the HCF using Euclid's Division Lemma or Euclid's Division Theorem. So see how to apply this theorem first. What is the theorem? A equal to BQ plus R, where R is 0 is less than equal to R less than B. Okay. So what will be the A? In this our example, what is important is how to decide the values of A, B and Q. Okay. So it is very important to focus on this concept, because if you take the wrong values of A and B, then you might not get the correct answer. Okay. So first focus on the theorem, how to apply this theorem. So value of A has to be greater than B. One most important thing here is A has to be greater than B. Here also you can write A has to be greater than B. These two conditions should be met. 0 is less than equal to R less than B, and A should be greater than B. Once you apply this theorem to the practical examples, then you will understand this concept more easily. So let us first apply this theorem. A equal to BQ plus R, value of R should be 0 less than equal to R less than B, and A should be greater than B. So what is the A should be greater than B? 455 is greater than 42. So this will be our A, this will be our B. So 455 equal to 42 into Q. So how to apply this theorem? A equal to BQ plus R. This is nothing but the generalized equation that we have seen in our previous worksheet. Dividend equal to divisor into quotient plus remainder. Euclid's division lemma is used to find HCF by using the concept of dividend and divisor. Okay. So in this theorem, A will be the dividend, B will be the divisor, Q will be the quotient, and R will be the remainder. So you might be hearing lot of sounds of birds and vehicles. This is 5 a.m. in the morning and we are recording this lecture, so excuse me for those background voice, birds and vehicles. You might be hearing those voices. So focus on this concept first. 455 equal to 42. So dividend will be A should be greater than B. So A, let us take greater number as dividend. A should be dividend. That is, greater number should be the dividend. 455 equal to 42 into quotient. What will be the quotient in this example? 42 into 10, you will get 420. And remainder will be 35. Now how to apply this theorem? We have to keep on applying this theorem until we get the remainder at 0. So in second step, what will be our dividend? It will be 42. In second step, you have to take the divisor as dividend and remainder as the divisor. So it will be 35 into 1. What will be remainder? It will be 7. So in second step we have taken as dividend as the divisor of previous step. So divisor of previous steps become dividend and remainder becomes divisor. This is the way to apply this theorem to find the HCF of given two numbers, and we have to keep on applying this theorem until the value of remainder is 0. Okay, in third step 35 will be our dividend because it is divisor. In second step, in third step it will be our dividend. Remainder will be our divisor. 7 into 5 you will get 35, so remainder will be 0. Never write in this form 5 into 7 because you have to write the divisor first and then only the quotient, otherwise you will get the wrong answer. So now as our remainder is 0, what is the value of divisor in this step? 7. So this will be our HCF. See here, by prime factorization method you have obtained the HCF as 7. So by applying Euclid's division lemma, here we have applied the Euclid's division lemma to find the HCF. In this method you don't have to do the prime factorization. Here you can directly apply the theorem and get the HCF. Suppose the numbers are large, within few steps you will get the HCF. So what will be the HCF? Once you get the remainder at 0, so the divisor in that particular step will be our HCF of given two numbers. This is the way to apply the theorem. So let us once again see how we have applied the theorem. A equal to BQ plus R. So what will be the A? A should be greater than B. So here 455 is greater than 42. So dividend will be 455, divisor will be 42, quotient will be 10 plus 35 will be remainder. Dividend equal to divisor into quotient plus remainder. This is the generalized formula which is used in Euclid's theorem as well. So 455 equal to 42 into 10 plus 35. So in second step the divisor becomes the dividend, remainder becomes the divisor. 42 into 35, 42 equal to 35 into 1 plus 7 will be remainder. Once you subtract 35 from 42 you will get 7 as remainder. In our third step, next step will be divisor. Here we have divisor as 35. This becomes the dividend. So dividend is 35 equal to 7. 7 is divisor. This is the remainder in previous step. So remainder becomes the divisor. Divisor becomes the dividend. Remainder becomes the divisor. So 35 equal to 7 into 5. 5 will be the quotient. Plus remainder is 0. 7 into 5, 35. 35 minus 35, you will get remainder as 0. So once the remainder is 0, that is value of R is 0, the divisor in this particular step will be our HCF. See, value of HCF is 7 by prime factorization. By using Euclid's division theorem also, HCF of 455 and 42 is 7. So let us again understand this concept in a detailed way. How does this method works? How does this method works? The Euclid's division lemma. Let us once again see the same example. HCF of 455 and 42. Euclid's division lemma. This is 0 should be less than equal to R less than B. and A should be greater than B. This is Euclid's division lemma. Let us write it here. You have to write these things in detail in your answer sheet, then only you will get the full marks. So apply this theorem one more time. A should be greater than B. 455 equal to 42 into 10 plus remainder is 35. Dividend equal to divisor into quotient plus 35 is remainder. Once you understand the basic formula of dividend equal to divisor into quotient plus remainder, then it will be very easy to apply the Euclid's division lemma. So in next step, our divisor becomes dividend, remainder becomes divisor. In this step it will be 42 equal to 35 into 1 plus remainder 7. So in next step, divisor becomes dividend, remainder becomes divisor. So 7 into 5, 35. 35 minus 35, remainder will be 0. So answer will be 7. HCF is 7. So why do we get an HCF by using this method? Once you focus on dividend and divisor in each step, you will understand that HCF of dividend and divisor in each step is constant. So this is the basic principle behind success of this Euclid's theorem. If you applied Euclid's division theorem to given two numbers, you will be getting the HCF. So what is the concept behind this? HCF of dividend and divisor in each step is constant. So if you find the HCF of 455 and 42, it is 7 by Euclid's division theorem. Now focus on the HCF of 42 and 35. If you find the HCF of 42 and 35 by prime factorization method, you will get answer as 7. Let us factorize 42. Now factorize 35. So what is the common common prime factor between these two factorizations? It is 7 and its least power is 7. So HCF of 42 and 35 is 7 by prime factorization method. So look at the HCF of dividend and divisor in each step. In first step we have given two numbers 455 and 42. So HCF of those two numbers is already we have calculated that as 7 by prime factorization method as well as using Euclid's division lemma. So in third step, if you find the prime factorization for 35 and 7, you will get HCF as 7. So HCF in each step is constant, which is 7. So this is the basic concept behind Euclid's division lemma. You have to remember two things regarding the Euclid's division lemma: the generalized form A equal to BQ plus R, where 0 is less than equal to R less than B, and A is greater than B. So this theorem is nothing but the generalized form of divider, divisor and remainder. So remember two things. First is apply Euclids division lemma. First thing is applied Euclids division lemma in such a way that dividend equal to divisor into quotient plus remainder. Okay. And second thing you have to remember is HCF of dividend and divisor in each step is common. Okay, this will be all about Euclids division lemma. Now we will see the Euclids division algorithm, which is nothing but the Euclids division theorem written in a stepwise form, that is in generalized form. You call that as an algorithm, which will help you to remember the steps you should apply while solving the problem. After seeing the Euclids division algorithm, we'll be solving few examples and then exercise 1.1. So just after one more theoretical worksheet, we'll be going to solve few examples related to this theorem. Now let us see the Euclids division algorithm. Euclids division algorithm is nothing but the stepwise form of Euclids division lemma or Euclids division theorem. So in this topic we are going to see the steps involved, that is the example that we have already seen. We put those steps in a generalized manner. This is called as Euclids division algorithm. You may be those who have studied these computer programming languages, they are familiar with the word algorithm. What is algorithm? Now what is the first see the first step of the Euclids division algorithm will be, we have to apply Euclids division lemma to given two numbers. In this case the two numbers might be, let's say, C and D. So we apply Euclids division lemma to numbers C and D. So we find whole numbers Q and R such that C equal to DQ plus R, 0 less than equal to R less than D. So these are the two numbers. C will be greater than D, so C equal to D into Q. Q will be quotient plus R remainder, such that 0 less than equal to R less than D. So this will be the first step. If you are given two numbers C and D, then you have to apply Euclids division lemma such that C equal to DQ plus R. These two numbers will be quotient and remainder. Now what will be the second step? If remainder is not 0, if R is not 0, then we will only proceed to second step. Otherwise, if R equal to 0, then D, the divisor in that step, will be the HCF of given two numbers C and D. If R is not 0, then that will be the final step and divisor will be our answer. But if R is not equal to 0, then we have to apply the Euclids division lemma once again to D and R. Remember that in second step the divisor becomes dividend and the remainder becomes divisor. So next time we have to apply the Euclids division lemma to D and R. There won't be any C in step 2. So step 1 and 2 will be continued till remainder is 0. The divisor at this stage where R equal to 0 will be the required HCF. Okay, continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Once R is 0, you will have your answer, that is HCF. The divisor in that step will be the HCF. So these are the 3 steps in which we will apply the Euclid's division algorithm. First you have to apply the Euclid's division lemma to given 2 numbers. If remainder is not 0, then in second step Euclid's division lemma will be applied to divisor and remainder, not the dividend. In second step it will be divisor will be dividend, remainder will be divisor. And you have to continue the process till you get the remainder 0. Once the remainder is 0, then in that step the divisor will be your answer, which is the HCF of given 2 numbers. This is the generalized form. I have already seen one example. This is just the generalized form of that process. It is called as Euclid's division algorithm. We can see it in the form of example. You can refer the previous example where we have applied the Euclid's division algorithm. What is the first step? In first step we apply the Euclid's division lemma to given 2 numbers C and D. So let's see the example. In first step, here 2 given numbers are 455 and 42. We have applied the Euclid's division lemma to given 2 numbers. What is the second step? Second step is, if remainder is not 0, if remainder is 0, you will have your HCF. If it is not 0, then you have to apply the theorem to D and R. So in second step, D will be 42, divisor will be dividend, remainder will be 35. So in this way you have to proceed till the remainder is 0. Once the remainder is 0, you will have your HCF as the divisor in that step, which is in this case 7. So this is the simplest concept, Euclid's division algorithm. Now let's see some examples based on this. Now let's see example 1. These are the examples from NCERT book. These are mentioned in theoretical part, not in the exercise. So already you have these solutions in your book. We are just repeating those. So if you have any suggestions regarding these lectures, you can always put those suggestions in comment section. Now let's see this problem. Use Euclid's algorithm to find the HCF of 4052 and second number is 12,576. So you have to find the HCF of these 2 numbers using Euclid's algorithm. Already we have seen the Euclid's algorithm. It is the 3-step process. So you have to apply the Euclid's division lemma in Euclid's algorithm. So these are the 2 given numbers. First we have to write the Euclid's division lemma, which is A equal to BQ plus R, where 0 is less than equal to R less than B and A is always greater than B. It is very important to write those steps because otherwise you won't get the full marks in examination. So never hesitate to write those things. Please write down the process in detail. If you are out of time, then you might skip 1 or 2 steps. But if you have time, then always put those every step in detail. So in this case, A and B 2 numbers are given. So A should be greater than B. So 12,576 is greater than 4,052. So A will be 12,576 and this will be B. So write down this. So how we are going to proceed? A will be 12,576 equal to 4,052 into Q. What will be the Q? That is quotient. You have to multiply 4052 in such a way that you will get certain remainder, so that you can put those things in a Euclids division lemma. So let me proceed with the solution. So if you multiply 4052 with number 3, then you will get the remainder as 420. So remainder is still not 0. This is the first step only. So you have to apply the Euclids division lemma once again. That is the Euclids algorithm. Euclids algorithm is you have to continue the process till the remainder is 0. So in second step, divisor will be the dividend, remainder will be the divisor, into quotient. If you multiply 420 by the number 9, then you will get the remainder as 272. Still the remainder is not 0. Then again apply. Then we have to again apply the Euclids division lemma. Divisor will be dividend. 420 equal to 272 into 1 plus 148 will be the remainder. Next step, divisor will be dividend. 272 equal to remainder will be divisor 148 into 1 plus remainder. What will be the remainder? 272 minus 148. You will get answer as 124. Now still the remainder is not 0, so you have to continue the Euclids algorithm, apply the Euclids division lemma once again. So in this step 148, in next step divisor will be dividend. 148 equal to 124 into 1, remainder will be 24. So still remainder is not 0. Again apply Euclids division lemma. 124 equal to 24. You have to apply it one more time because the remainder is not 0. So 124 will be the dividend, remainder will be the divisor. What will be the quotient in this case? You will have the quotient as 5. 24 into 5. So if you subtract this product will be 120. The remainder that you will be getting in this case will be 4. So still remainder is 4. So in next step divisor will be dividend. 24 equal to remainder will be divisor into quotient will be 6. Why? 6 into 4, 24. 6 plus remainder will be 0. So once the remainder is 0, this will be our final step, and the divisor in this case will be our answer. So it is very important to write in this form, divisor into quotient. If you change this order, then you might get the wrong answer. See, if you change the order, then your answer will be 6. So that will be a wrong answer. So you have to always follow the order. It will be always divisor into quotient. So once the remainder is 0, the divisor will be our answer. So HCF of given two numbers 12,576 and 4,052 will be 4. This is our answer. HCF of 12,576 and 4,052 will be 4. So let us see the process one more time. You have to apply Euclid's algorithm to find the HCF of given two numbers. What is the Euclid's algorithm? You have to apply the Euclid's division lemma till the remainder in this formula becomes 0. That is Euclid's algorithm. So in first step, always write the formula for Euclid's division lemma. So A equal to BQ plus R, 0 less than equal to R less than B. A is always greater than B. So in our case, A is greater than B. So A will be 12,576. B will be 4,052. Okay. So apply the Euclid's division lemma to given two numbers. So A equal to BQ plus R. 12,576 will be A. B will be 4,052. What will be the quotient? You have to decide the quotient by trial and error method. If you multiply 4,000 with 3, you will approximately get the answer as 12,000. You will get 12,000. So in that way you have to decide the quotient. So in this case quotient will be 3. So if you multiply this and subtract from 12,576, you will get remainder as 420. You can see it here. 12,576, 4,052 into 3 will be so if you subtract these two numbers, you will get the remainder as 420. That is the remainder here. In second step, still remainder is not 0, then repeat the Euclid's algorithm. Apply the Euclid's division lemma one more time. So in second step, divisor becomes dividend, remainder becomes divisor. In this case, how to decide the quotient? 420, here you have 4,000 something. So if you multiply this divisor by 9 into 400, you will get approximately 3,600 answer. So that will be close to our required number. So we have taken quotient as 9. So the remainder will be 272. Still remainder is not 0. Next step, remainder will the divisor will be the dividend, remainder will be the divisor. You have to decide the quotient. If you multiply 272 by 2, then it will be greater than 420. So you have to take the quotient as 1 only. This process is nothing but, let me write this one here. If you divide 4,052 by 420, let's see this step. It will be 9. 9 will be the quotient, and you have to multiply this product. You have to subtract this product and from this number. So then you will be getting the remainder as 272. So what will be the product of these two numbers? correct. It will be 3780. So remainder in this case will be 272. This is the number here. So what is this formula? Dividend equal to divisor into quotient plus remainder. Already we have seen this process. We are just repeating those steps. Okay. So in this step, divisor becomes dividend, remainder becomes divisor. So quotient will be 1, remainder will be 142. In next step, dividend will be 272, divisor will be 148, quotient will be 1, because if you multiply by 2, then it will be greater than 272. So it has to be 1 only. Remainder you will be getting is 124. Now next step, the dividend becomes 148, divisor 124, remainder 24. In this step, divisor becomes dividend 124, remainder becomes divisor 24. 24 into 5, you will be getting remainder as 4. And in last step, 24 becomes dividend, remainder becomes divisor as 4. 4 into 6, 24. 24 minus 24, 0. Remainder will be 0. Once the remainder is 0, you have to stop the Euclid's algorithm. And the divisor in that case, in that step, will be your final answer. That is 4. HCF of given two numbers will be 4. You can cross check this answer by prime factorization method. You can factorize these two numbers and take the least power of common prime factors from those prime factorizations, and you can find the HCF by prime factorization also, but that will be a lengthy process. This is the short process. Only thing is you have to understand it clearly. This process, the basic formula, basic concept in this case will be, always remember a simple formula: dividend equal to divisor into quotient plus remainder. Euclids division lemma is nothing but dividend equal to divisor into quotient plus remainder. So this is within 4 or 5 steps you have got the answer as 4. HCF of given two numbers is 4. Now let's see a few more examples based on this. Let's see second example. This is also from the textbook only. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. So what is asked in this example is, you have to show that every positive even integer has the form 2q and every positive odd integer, in this case even integer 2q, and the every positive odd integer will be 2q plus 1. So how to solve this problem? So you have to, it is obvious that you have to use the Euclids division lemma. So before that you have to make an assumption that a be any positive integer. It might be even or odd. Let a be any positive integer. It might be even or odd. It can be even or odd. It is any positive integer, so it will be even or odd. Now apply Euclids division lemma. Any positive integer. That means it can be a even number or it can be a odd number. So write down the Euclids division lemma. Euclids division lemma. It is very important to write these steps. This way you will understand you will remember the concept in a better way. What is Euclids division lemma? A equal to BQ plus R, where 0 less than equal to R less than B, and A has to be greater than B. So in this case, the number you have given, value of B will be 2. It is given, value of B is given in this case. See, here you have 2, here there is some number plus 1, this will be the remainder. So value of B equal to 2 is given. Now write down the generalized form. A equal to 2Q plus R. Now 0 less than equal to R less than 2. Why you have written the value of B as 2 in those steps? In this formula we have used the value of B, and here also in this condition also you have used the value of B as 2. So what are the possible values of R? R has to be less than B, and it can be greater than or equal to 0. So possible values of R will be 0 or 1. These are the only two possible values which can be used in place of R, because it has to be less than 2 and greater than or equal to 0. So it can be either 0 or 1. So you will get two equations, A equal to 2Q or A equal to 2Q plus 1. Here value of R will be 0, then you will get the first number as 2Q. If we put 1 in place of R, then second number we will be getting is A equal to 2Q plus 1. In place of R we have used the 1, so it will be 2Q plus 1. So second number will be 2Q plus 1. So these are the two possible values of any positive integer. So already we have got our answer. Only thing is you have to write in a detailed manner. See, what here mentioned is every positive even integer has to be of the form 2Q. So it is obvious, if you multiply any number by the value 2, then it will be a resultant product will be an even number. So this has to, the A has to be a even number only, because we have to multiply the value of Q by 2, then it resultant will be even number. So let me write this in here. If A equal to 2Q, then A is even integer. If A equal to 2Q, then A is even integer. Second, positive integer can be even or odd. So any the positive odd integer is of the form, if A equal to 2Q plus 1, A equal to 2Q plus 1, then obviously 2Q is a even number. If we add a value 1 to any even number, then it will be an odd number. Let's say q will be 2. 2 into 2, 4. 4 plus 1, you will be getting 5. So a will be 5, which is an odd number. So this way, if a equal to 2q plus 1, then a is a positive odd integer. This is the final answer. You have to write in this form. So let's see one more time what we have done here. We have given a problem here. You have to prove that every positive even integer is of the form 2q. Every positive odd integer is of the form 2q plus 1. This is the simplest process. First, we have assumed that a is any positive integer. It can be even or odd. So we have assumed an letter a as any positive integer. Okay. Now apply the Euclids division lemma. What is Euclids division lemma? A equal to bq plus r. 0 less than equal to r less than b. A has to be greater than b. Value of b is already given in the problem, which is 2. So replace the value of b in this equation as well as in this condition. So what we will be getting is a equal to 2q plus r, 0 less than equal to r less than 2. Value of b will be 2. Now what are the possible values of r? R has to be less than 2 and greater than or equal to 0. So possible values of r will be 0 and 1 only. So put these two values in this equation and you will get these two separate equations. If we put 0 in place of r, then we will get the first value as a equal to 2q. If we put r equal to 1, then we will be getting the second number as a equal to 2q plus 1. Now if we multiply any number by value 2, then it will be a even number. If a equal to 2q, then this will always be a positive even integer. So this is our answer. Positive even integer is of the form 2q. If a equal to 2q, then a is even, positive even integer. Positive even integer. If we add 1 to value 2q, then it will be obviously a odd number. If you add 1 in any even number, then it will be a odd number. If we add 1 to 4, 4 plus 1, 5. Similarly 13 plus 1, 14, like that. That's why if a equal to 2q plus 1, then a is a positive odd integer. You have to write these separate two statements, then only your answer will be final, because all this process has no meaning unless you write these two sentences. Always write every step and then you will understand the given problem. It will be easier for you. So let's see the next example, example 3. In problem example number 3 also, we need to use the Euclids division lemma to solve the given problem. So let's look into the example 3. Example 3 says show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. So in this example we have to show that any positive integer has the form of 4q plus 1 or 4q plus 3. It is similar to the previous example. Only thing here is that in a previous example we have shown that every positive odd integer is of the form 2q plus 1. So in this example we have to show that any positive odd integer is of the form 4q plus 3 or 4q plus 1. So let's look into this problem. First you have to assume that any positive integer and accordingly apply the Euclid's division lemma to that integer. So now let's assume let a be any positive odd integer. Let a be any positive odd integer. So now let's just apply the Euclid's division lemma. Euclid's division lemma. A equal to bq plus r, where 0 is less than equal to r less than b and a is greater than b. So value of b is given here, which is 4. Given. So value of r might be, value of r is less than b and greater than or equal to 0. So value of b will be 0 or 1 or 2 or 3. So any of these 4 values can be assigned for r. So if we use 0 or 2 in place of r, then our answer will be, let's just say, what are the forms a can take? A equal to bq, b is 4q plus r. R can be 0, 1, 2 or 3. Less than 4. R has to be less than 4 and greater than or equal to 0. So R can take values of 0, 1, 2, 3. Not 4, it has to be less than b. So it will be 3 only. It can take only integer values. So a can be 4q plus 0 or 4q plus 1 or 4q plus 2 or 4q plus 3. So 4q and 4q plus 2, these are the two numbers. This is 4q and 4q plus 2. Let's write here 4q and 4q and 4q plus 2 are divisible by 2, are divisible by 2. So they cannot be odd integers because our assumption is a is any positive odd integer. So it has to be either 4q plus 1 or 4q plus 3. Let's just see this concept. 4q and 4q plus 2 are divisible by 2. How? If we multiply any number by 4, then it will be a even integer. So that is not our requirement. We need positive odd integer. So 4q, if we multiply 4 by 3, then it will be 12. It is again even number. If we add plus 2, then it will be 14. Then again it is a even number. So our requirement is it has to be a positive odd integer. So 4q and 4q plus 2, these are the forms which will give you always a even number. What does this mean? R divisible by 2 means it is a even number. Hence R even numbers. Hence any positive integer, any positive odd integer can be of the form, is of the form, is of the form 4q plus 1 or 4q plus 3, because 4q and 4q plus 2 are even numbers. Hence our answer will be 4q plus 1 or 4q plus 3. This is the final answer. You have to write each step in detailed manner so that you get the full marks. Let's revise this problem one more time. What is asked here is we have to show that every positive integer has the form 4q plus 1 or 4q plus 3. So we have assumed that a be any positive odd integer. Okay, then we have applied the Euclids Division lemma. Just write down the formula a equal to bq plus r, where r is 0 less than equal to r less than b and a is greater than b. So value of b given here is 4. You can see here it is given. So r has to be less than b and greater than or equal to 0. So value of r can be 0 or 1 or 2 or 3. So what are the 4 possible forms of a? You have to replace r by these 4 values and you will get the 4 corresponding equations. So a can be 4q plus 0 here. A can be 4q plus 1, 4q plus 1, or a can be 4q plus 2, 4q plus 2. We have just replaced the value of b by 4 and r by 2. Now replace b by 4, it will be 4q, and r by 3, it will be 3. So 4q plus 3. So out of these 4 equations, 4q plus 0 and 4q plus 2 are always divisible by 2. Why is that? Because 4q is always a positive even integer and 4q plus 2 will always be positive even integer, so they are divisible by 2. If we multiply any number by 4, then it will be an even number. If we add 2 to that number, then again it will be an even number. You can try by replacing any number in place of q and see, you will get an even number only. Suppose q is 3, then you will get 4q as 12. It is a even number. If we add 2 to 12, then again it will be 12 plus 2, 14. Again a even number. So these two are always be even numbers. So that is not our requirement. We need positive odd integer. So what are the remaining two values? 4q plus 1 and 4q plus 3. So these are the two forms. So that is our required answer. Any positive odd integer is of the form 4q plus 1 or 4q plus 3, because remaining two forms are of even numbers. So this can be our answer. 4q plus 1 or 4q plus 3 will be the form of any positive odd integer. Okay, let's look into the problem number 4. This is our example number 4. Let's read the statement first. A sweet seller has 420 kaju burfis and 130 badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that burfis can be placed in each stack for this purpose? So what is asked here is, one sweet seller, she sells kaju burfis and badam burfis. So she has 420 kaju burfis and 130 badam burfis. She wants to stack them in a tray in such a way that it occupies least area of the tray. Here, least area of the tray. So if we place maximum number of burfis in each stack, the number has to be equal, and then the area of the tray will be minimum. So what is the, we have to stack maximum number of burfis in each stack, so it has to be a HCF. What is asked here is, how do you find it out? The area of the tray, least area of the tray. Let's write this down. The area of the tray used, the area of the tray used or you can say occupied. Area of the tray used should be minimum that is given. Hence, we need to find HCF. Why? Because we have to, once you place maximum number of burfis in each stack, then it has to be a HCF only. Then only the area occupied will be minimum or least. So what is asked here is, you have to find HCF. So how to find HCF of 420 and 130? You will get the maximum number of burfis that can be put in each stack so that the area occupied will be minimum. So you can apply the Euclids division lemma right here. Euclids division lemma. A equal to BQ plus R. 0 less than equal to R less than B. A is greater than B. So let's write here 420 equal to 130. What are the values of A and B? 420 and 130. A has to be greater, so it will be 420 equal to 130 into, what will be the quotient? If we multiply 130 by number 3, then you will get 390. So it is around 420. So quotient will be the 3 plus what will be the remainder? 130 into 3, it will be 390. 420 minus 390, R will be 30. Okay, so value of R is 30. Now in second step, replace divisor as dividend, remainder as divisor, into quotient. What will be the quotient? If we multiply 30 by 44, multiply 30 by 4, it will be 120. So it is around 130. So 30 into 3 plus it will be 90. 130. Okay, sorry. You can multiply 30 by 4 directly. It will be around 120. It will be 120. So it will be around 130. So 30 into 4, 120. 130 minus 120, it will be 10. So again, in next step, divisor becomes dividend, remainder becomes divisor. 10 into 3, 30, it will be exact number, so 30 minus 30, remainder will be 0. Once the remainder is 0, we got our HCF as the divisor in this step, which is 10. So HCF of 420 and 130 is 10. So write down the detailed answer here. Okay, we have to write how many Murphys can be placed in each stack. Ten Murphys can be put in each stack. So you have to write it in detail so that the examiner, the person who is checking your answer sheets, will know that you understood the concept. 10 Murphys can be put in each stack so that area of the tray will be least occupied. So this statement is also important, because the examiner will know that you have found the HCF to find the number of Murphys in each stack. So let's revise this problem one more time. What is asked here is, a sweet seller, she wants to put 420 Kaju Murphys and 130 Badam Murphys. She wants to stack them in such a way that area of the tray occupied should be least. So when will be the area occupied least? We have to put the maximum number of Murphys in each stack. It is a simple concept. This is important. Once you understand this statement, that we need to find the HCF, then that will lead you to the correct answer. So how to find the HCF? We have the Euclids Division lemma to find the HCF quickly. So first write down the Euclids Division lemma. A equal to BQ plus R, 0 less than equal to R, less than B, A is greater than B. So what are the values of A and B? The number of Murphys. 420 will be A, 130 will be B. So what will be the quotient in this example? 130 into 3, it will be 390. So 420 minus 390, you will get remainder as 30. So it is not 0. So we have to continue the process till the remainder is 0. The R value of R should be 0. Then only you will get the HCF as your final answer. So in second step, value of divisor becomes division, remainder becomes divisor. 30 into 4, 120. 130 minus 120, you will get remainder as 10. So in this step, 30 will be divided, 10 will be the divisor. So 10 into 3, 30. 30 minus 30, remainder is 0. Once the remainder is 0, you got your HCF as 10. got the HCF as 10. It is the last step. So this is our required answer. We need to find the HCF, which is the maximum number of burpees which can be stacked in each stack, so that the minimum area of the tray will be occupied. So 10 burpees can be put in each stack so that the area of the tray will be least occupied. You have to write this statement at the end so that you will get the full marks. So these are the 4 examples which are already given in your book, NCERT book. So we have to now solve the exercise 1.1. There are total 5 problems. Most of them can be solved by using Euclid's Division lemma. So let's look into those problems. Once those 5 problems are over, then we'll have the end of our second lecture. So let's start with the exercise 1.1. You have total 5 problems in exercise 1.1. So after that, this second lecture will be over. So there are 5 problems in exercise 1.1. So let's start with the first example. Use Euclids Division algorithm to find the HCF of these 3 pairs. You have to apply the Euclids Division algorithm to these problems. So what is the first problem? 135 and 125 to find the HCF. So Euclids Division lemma. Write down the Euclids Division lemma first. Euclids Division lemma. A equal to BQ plus R, where 0 is less than equal to R less than B, A should be greater than B. So what are the values of A and B? 135 and 125. A should be greater than B, so value of A should be 135. So 135 equal to 125 into what will be the quotient? It will be 1, because if you multiply by 2, then it will be 250, which will be greater than B, the value of A, 135. So that is not possible. So 125 into 1, you will get remainder as 10. What will be the remainder in this case? Sorry, the example given in your book is 135 and 225. Okay, it has to be 225. So value of A should be 225. A is greater than B, so A should be 225. It should be 225 equal to 135, sorry for the inconvenience, into 1. You will get remainder as 90. These two numbers are 135 and 225. So A should be greater than B, so we have written the 225 as A, 135 as B, quotient will be 1. What is the remainder? 225 minus 135, it will be 90. So in next step, our dividend becomes the divisor of previous step. 135 equal to remainder becomes divisor 90 into 1 plus what will be the remainder? It will be 45. 90 into 1, 90. 135 minus 90, it will be 45. Apply, then remainder is also not 0, then we have to apply the division lemma one more time. 90 equal to 45, what will be the quotient? 45 into 2 will be 90, plus remainder will be 90 minus 90, it will be 0. So HCF will, this once the remainder is 0, you got your answer as 45, the divisor in that step. So HCF of 135 and 225 is equal to 45. This is our final answer. We have already learned how to apply the Euclids division lemma. Only thing we got here is value of A and B. You have to put those values in Euclids division theorem and apply the Euclids division algorithm till value of R is 0. You got your HCF as 45. Okay, let us look into the second example. 196 and 38,220. There is little space available here, so we will make the partition here. So what are the values of A and B? 196. A should be greater than B, so value of A should be 38,220. Value of B should be 196. So if we try to factorize this, it will take you a lot of time. So once you apply the Euclids division lemma, you can obtain the HCF within few steps. Okay, apply Euclids division lemma. A equal to BQ plus R, 0 less than equal to R less than B. A should be greater than B. Once A should be greater than B, then 38,220 will be our A. Value of B will be 196. What will be the remainder? You have to find out the remainder by trial and error method. Let's just say if you multiply 196 by number 100, you will get 19,600 as your answer. If we multiply it by 200, it will be 392 into 100. Like if you multiply 196 by 200, it will be 33,000. Around that, the value of what will be the answer? You have to find the quotient value by trial and error method. So if we multiply 196 by number 200, it will be around 39,000. So you have to find out 196. If you divide 38,220 by 196, the quotient will be 195. This will be only one step answer. So if you multiply these two numbers, you will get exactly 38,220. So remainder in this first step itself will be 0, because 38,220 minus 196 into 195, it will be same number, 38,220. So this will be, remainder will be 0. In first step itself, you got your answer as HCF of 196 and 38,220 will be the divisor itself, which is 196. In one step only you got your answer. So only difficult thing in this step is you have to find the quotient by trial and error method. You have to use your rough sheet and find out the quotient. Once you find out the quotient, then the remainder in this step becomes 0 in first step itself. So your answer will be 196. You have to write this in this order only, 196 into 195. If you change the order, your answer will change, which will be a wrong answer. So apply the division lemma in exact form. It should be divisor into quotient always. Divisor is 196, which is value of b, and that is our answer, 196. Now let's look into the third problem. $867 and $255. By Euclids Division lemma, A equal to BQ plus R, where 0 should be less than equal to R less than 0 is less than equal to R, 0 less than equal to R less than B, and A should be greater than B. So what are the values of A and B? A should be 867. A is greater than B. 867 and 255. 867 equal to 255 into what will be the quotient here? It will be 3. If you multiply 250 by 3, it will be around 867. Not exactly 867. If we subtract 867, if we multiply 255 and 3 and subtract that value from 867, you get the remainder as 102. So again, in second step, the divisor becomes dividend. It is 255 equal to 102 into 2. The remainder, what will be the remainder in this step? It will be 51. 102 into 2, it will be 104. You have to subtract that from 255. You will get remainder as 51. Again, in third step, (51) into 2 plus 0. Remainder in this step is 0. So HCF of 867 and 255 is 51, the divisor in this case. So what is our required answer? It is 51. Once the remainder is 0, the divisor in that step becomes our HCF, which is 51. Okay, let's just stop here. Let me draw one line here because below we have problem number 2. Okay, now let's look into the question 2 of exercise 1.1. This is our question 2 of the exercise 1.1. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So already we have solved a few examples like this one. So let's start with the solution. What we have done in previous examples is to assume some number as any positive odd integer. Let a be any positive odd integer. Positive odd integer. So write down the Euclids division lemma. By Euclids division lemma, A equal to BQ plus R, 0 is less than equal to R less than B, A should be greater than B. Value of B given here is 6. B equal to 6, which is given. So value of R should be less than B but greater than or equal to 0. So it can take values 0 or 1 or 2 or 3 or 4 or 5. R can be these. R can take these 5 values: 0, 1, 2, 3, 4, 5. So how to proceed in this case? A can be 4Q, 6Q plus R. R is 0, so it will be 6Q, or 6Q plus 1, or 6Q plus 2, or 6Q plus 3, or 6Q plus 5, or 6Q, no, this will be 4, 6Q plus 4, or 6Q plus 5. So 6Q plus let's just say these you have to now shortlist these 3 equations. If we add 0 to 4 to 6Q, 6Q plus 2 and 6Q plus 4. So these 3 equations, consider these 3 equations: 6Q, 6Q plus 2, 6Q plus 4. These 3 equations, these are divisible by 2. 0 to 4. If you add 0, 2 or 4 to 6Q, then it will be a positive integer. That is not our requirement. We need positive odd integer. If we multiply any number by 6, it will be a even number. If we add 0, 2 and 4 to that number, it will be again an even number. But we need positive odd integer. So these 3 numbers are divisible by 2, hence positive even integers. Hence any positive odd integer is of the form six q plus remaining 3 numbers: 6Q plus 1, 6Q plus 3 and 6Q plus 5, or 6Q plus 3 or 6Q plus 5. This is our final answer. Let's look into the example one more time. You have to show that any positive integer is of the form 6Q plus 1, 6Q plus 3 or 6Q plus 5. Okay, where Q is some integer. So we have to assume any positive odd integer. Let A be any positive odd integer. Apply the Euclids division lemma. Value of B is given as 6. So value of R should be less than 6 and greater than or equal to 0. So value of r can be from these 5 integers 0, 1, 2, 3, 4, 5. Correspondingly, if we replace the value of r by these 5 numbers, you will get corresponding 5 equations. Out of these 5, 6q, 6q plus 2 and 6q plus 4. These 3 equations, if we put any number in place of q, you will get the answer as positive even integer because they are divisible by 2. If you add 0 to 4 to 6q, 0 or 2 or 4 to value 6q, it will be always a positive integer, positive even integer. Hence this cannot be our answer because what we need is positive odd integer. So obviously remaining 3 numbers will be positive odd integers. So hence our answer is any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5. This will be all about our problem number 2. Now let us look into the problem number 3 of exercise 1.1. So let's start with the example 3 of exercise 1.1. An army of contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So an battalion or contingent of an army is moving with 616 members. They have to march behind an army band of 32 members. It is 32 members in a parade. So the two groups are to march in same number of columns. What is the maximum number of columns in which they can march? So these 32 members will be at the front side and behind them it will be other 616 members. So you have to find out maximum number of columns in which they can move. So you know the army discipline. They march in, generally their arrangement is in very systematic manner. So here they have to move behind these 32 members, these 616 members. So the number of columns should be same for these 32 members which are on the front side, and 616 members on the end of the column. So these two members, you need to find the maximum number of columns in which they can move so that they have same number of soldiers in each column. So these 616 members are moving behind these 32 members. Okay, so in order to have the maximum number of columns, the soldiers in each column has to be minimum. Once the soldiers are minimum, you can increase the columns. So what is important here is this last line, maximum number of columns in which they can move. So for maximum number of columns, we need to find, in this case, what will be our required answer. In this case, we need to find the LCM of that number or HCF of that number. That is the important concept in this case. So here we need to find maximum number of columns. So for maximum number of columns we need to find the HCF. Okay, so how to proceed with this problem? You can use the Euclids Division lemma to find the HCF. We need to find the HCF. So what are the two numbers given here? 616 and 32. So once you find the HCF, you will get the maximum number of columns in which they can move. So by Euclids Division lemma, A equal to BQ plus R, 0 less than equal to R less than B, A should be greater than B. What are the values of A and B? A should be greater than B, so A should be 616, B should be 32. If we apply Euclids division lemma in this case, then value of Q should be, in this case you can write plus R, so 616 equal to 32 into, you can take quotient as 9, you will get remainder as 8. So 32 equal to 8 into 4 plus 0. Within 3 steps you got your answer as 8. HCF equal to 8. HCF equal to 8. Write down it in this manner. HCF of 616 and 32 equal to 8. HCF, once the remainder is 0, you will have your HCF as divisor in that step. So HCF of 616 and 32 is 8. So write down the final answer. Maximum number of columns in which the army contingent can move for a given number of members, that is 616 and 32 is 8. You have to write in detail, because then only it shows that you understood why we have found the HCF. Okay, so let's look into this one more time. What is asked here is 616 members has to move behind these 32 members. You have to find the maximum number of columns in which they can move. So for maximum number of columns we need to find the HCF. Okay, so what is the best way to find the HCF? Apply the Euclids division lemma. So what are the given numbers? 616 and 32. So if you apply Euclids division lemma to these two numbers, you will get HCF as 8, and that will be our final answer for number of columns. So maximum number of columns in which the army contingent can move for given number of members is 8. So let's look into the question number 4 of exercise 1.1. In question number 4, let's read the statement given. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So hint is also given in your book. How you can proceed. Let x be any positive integer, then it is of the form 3q plus 3q plus 1 or 3q plus 2. Now square each of these and show that they can be rewritten in the form 3m or 3m plus 1. So first you have to assume that x be any positive integer. Show that this can take these three equations. You get these three equations, and then if you square them, you will get either of these two forms. So let x be any positive integer. So by Euclid's division lemma, the answer will be quite lengthy one. Euclid's division lemma, a equal to bq plus r, 0 less than equal to r less than 0 less than equal to r less than b, and a should be greater than b. So what will be the value of a? It will be x. We have assumed that x be any positive integer. So x equal to, what is the value of b given? What is the value of b given? It is 3. Value of b given here is 3. So it will be 3q plus r. What are the possible values of r? It should be less than 3 and greater than or equal to 0. So it will be 0, 1 or 2. So x equal to 3q plus 0, it will be 3q, or 3q plus 1, or 3q plus 2. Now what is the hint given here? Now square each of these and show that the final answer is 3m or 3m plus 1. So you have to square these equations. Take the square of these equations and you will get the generalized form. So x equal to 3q square or 3q plus 1 square. You have to take square of this both sides. So it will be x square equal to 3q square or 3q plus 1 square or 3q plus 2 square. So if you square all these three equations, you will get the answer as 9q square or 9q square plus 6q plus 1 or 9q square plus 12q plus 4. What is a plus b square? It will be a square plus 2ab plus b square. So what is 3a square? What is 3q square? It is 9q square. Now a into b into 2ab. So it will be 12q and square of 2 will be 4. Okay. This is not part of the solution. I have written the generalized formula here only. So value of x square can be of these three forms. So let's just generalize this equation. If we take 3 out of 9q square, it will be 3 square, 3 into 3q square. Or you can take 3 common from these two numbers, 3 into 3q square plus what will be the multiple of q here? It will be 2q. 3 into 3 9, 9's q square you got. Now 3 into 2 6, you got the 6q plus 1. Or here you can take again 3 as common factor, 3 into 3q square plus 4q plus 4. This can be your common factor here, 3. So once you replace these 3 brackets with the generalized form, then you might get your final answer. So here we have to make one little bit adjustment. This cannot be the final form, because if you take 3 common, you can take 3 common from this 4 value also. So it has to be 3 into 3q square plus 4q plus 1, and here again you have to add 1. So what will be the multiplication? 3 into 3, 9q square, 3 into 4, 12, 12q, 3 into 1, 3, plus 1, 4. Here we have to add 1 to this multiplication. 3 into 1, 3, plus 1, already you have written it. So it will be 4 again. So if you look into this, you have the generalized form as 3 into some factor, 3 into some factor plus 1, or again 3 into some factor plus 1. So these two forms are similar. Only thing is, here we have 3 into some factor plus 1. Again here you have 3 into some factor plus 1. So these two forms are identical. Only thing changed here is the value in the bracket. So you can replace this by 3 into k1 or 3 into k2 plus 1 or 3 into k3 plus 1. You can take k, or directly you can take the value of m. You can write as you wish. It got out of the screen. Let me write it one more time. Let me tell you this step one more time. So if we take 3 common, it will be 3q square. See this equation, 3 into 3, 9q square. You can take 3 common from these two numbers. 3 into 3q square, you got 9q square. 3 into 2q, you got 6q plus 1 as it is. Now what is the third equation? 9q square plus 2q plus 4. You can take 3 common from these 3 numbers. So 3 into, what will be, here we got little bit messy here. So it will be, if we take 3 common, it will be 3q square. It will be 4q. For 12q it will be 4q. And again from if we take 3 common from this third number, it will be 1. So let's look into this product. 3 into 3q square, you got 9q square. 3 into 4q, you got 12q. 3 into 1, 3 plus 1, you got the third number as 4. 3 into 3, 3 plus 1. It will be 4. So if you look into these 3 equations, you got 3 into some factor for first equation, 3 into some factor plus 1 for second equation, 3 into some factor plus 1 for third equation. So these two forms are equal. Why? Because here you got 3 into some factor plus 1. Here again you have 3 into some factor plus 1. Only thing changed here is the value in the bracket. So let's write this in generalized form. It has to be 3m, or you can say 3m. You can assign values as m1, m2 or m3. 3m3 plus 1. What are the m1, m2, m3? These are the values given to these brackets. If we replace 3q square with m1, you got 3m1. If we replace 3q square plus 2q by m2, you got 3m2 plus 1. And similarly for this one, you got 3m3 plus 1. So look at these two forms, 3m2 plus 1, 3m3 plus 1. These two forms look similar. So here we have, let's write this down here. We have limited space here, where m1 equal to 3q square, m2 equal to 3q square plus 2q. You have to write in detail, then only the examiner will know what are the values of m1, m2 and m3. 3q square plus 4q plus 1 plus 1. Now replace m1, m2, m3 by generalized form which is asked in our example, which is 3m or 3m plus 1. Because here you can see easily these two forms are equal. Only thing changed here is m2 or m3. Okay. Hence, square of any positive integer, square of any positive integer is of the form 3m or 3m plus 1. This is our final answer. So let's look into this problem one more time. What was asked here is you have to show that square of any positive integer has these two forms. Square of any positive integer is of the form 3m or 3m plus 1. So we have assumed one letter as positive integer. So let x be any positive integer. So x is a number which can be any positive integer. By Euclids Division lemma, now apply the Euclids Division lemma. Replace a by value x, and value of b given is 3. So if you apply the Euclids Division lemma, you got these three equations. R can be 0, 1 or 2 because value of b given here is b equal to 3, which is given. Okay. So R can be 0, 1 or 2. So correspondingly you got three equations, 3q plus 0, 3q plus 1, 3q plus 2. So you have to take the square because we have to prove that square of these positive integers is of the form 3m or 3m plus 1. So we have taken the square of both sides. X square equal to 3q square or 3q plus 1 square or 3q plus 2 square. You have to write those squares in detailed form. Now take common factor out of those equations. So here you can take 3 common. 3 into 3q square, it will be 9q square. 3 into 3q square plus 2q. So if we take 3 common from these two numbers, it will be, in bracket we got 3q square, and if we take 3 common from this number, it will be 2q. So you can see that these two equations are same. 3 into 3, it will be 9q square. 3 into 2q, it will be 6q plus 1 as it is. Here also you can take 3 common from all these three numbers. So in bracket you got 3q square plus 4q plus 1. And again here you have 4, so 3 is taken common, so you have to add 1. So 3 into 3q square, it will be 9q square. 3 into 4q, you got 12q. 3 into 1, 3, you got 3 plus 1, it will be 4. So if you replace these brackets with values m1, m2, m3, then you got this generalized form. It has to be 3m1 or 3m2 plus 1 or 3m3 plus 1. So m2 and m3 are constants. So these two forms are similar. Okay. So you can replace these three equations by only 2. Then the final answer will be any square of any positive integer is of the form 3m or 3m plus 1. For these two equations you can write common factor as 3m plus 1. So this will be our final answer. Let's look into the problem number 5 of exercise 1.1. So this is the last example from the exercise 1.1. Here you have given the statement where it says use Euclids Division lemma to show that the cube of any positive integer is of the form 9m plus 1, 9m or 9m plus 1 or 9m plus 8. You have to show that cube of any positive integer has these three forms, one of these three forms. So before proceeding with the equation, let's assume let a be any positive integer. This is always the first step. By Euclid's division lemma, you got here a equal to bq plus r, where 0 is less than equal to r, less than b. A has to be greater than b. So what is the value of b? This is the important step in this equation, because if you take value of b as 9, then correspondingly you get 9 values of r, for which you have to solve almost 9 equations. So it might take half an hour to solve those equations. So what is the adjustment or the short step here is, you have to understand that any number which is divisible by 9 is also divisible by 3. Let us write it down here. Any number which is divisible by 9 is also divisible by 3. Hence b equal to 3. So by applying this concept, we have reduced the value of b from 9 to 3. So if b equal to 3, correspondingly you got values of r as 3 different numbers. So the number of equations are now reduced from 9 to 3, which is a lot more easier for you to solve the problem. So what is the important step in this equation, in this problem, is you have to take the value of b as 3, because it will help you to solve the problem in a few steps. So let's write down the further steps for Euclid's division lemma. So value of b is 3. So rewrite the equation a equal to 3q plus r. So what are the values of r then? R has to be less than 3 and greater than or equal to 0. So r will be 0 or 1 or 2. So a will be equal to 3q plus 0 will be 3q, or you have or 3q plus 1. Replace r by these three values, or 3q plus 2. So you have to show that cube of these three numbers is of the form 9m or 9m plus 1 or 9m plus 8. So take cube of all these three equations. A cube equal to 3q cube or 3q plus 1 cube or 3q plus 2 cube. So let us write down these equations in detailed form. I have to make a partition here. So it has to be, what will be the value of a cube? It has to be 3q whole cube. So it has to be, what will be the value of this equation? It will be 27q cube, or a cube equal to, you can write it in so these are the three expansions of these three equations. Let me explain it to you one more time. 3q cube, it will be 27q cube. 3q plus 1 whole cube, it will be this equation. Use this generalized equation formula to expand these equations. Okay, here also third equation, 3q plus 2 whole cube will be this equation. So if you look into these equations, you can easily take out 9 as the common factor from these two equations. Okay, so what will be the final form you will be getting? A cube equal to 9 into 3q cube, or 9 into 3q cube plus q square plus q plus 1, or 9 into 3q cube plus, take common 9 from this equation, 3q, you will get 3q cube plus 2q square plus 4q, here you have 8 also, plus 8. So these are the three equations you will be getting. So if you replace these brackets with a constant, then you will got the required answer. So again I have to make one more partition here. Hence cube of any positive integer is of the form 9m or 9m plus 1, write down or 9m plus 8. Okay, so let me explain it to you one more time. The solution got little messy here, messed up. There is little space available. Next time I will draw it on a bigger sheet. So let me explain it one more time. Here value of a has to be any positive integer. What is given here is you have to show that any positive cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So we have assumed a as any positive integer, applied Euclids division lemma. So important step here is, instead of taking value of b as 9, take value of b as 3, because any number which is divisible by 9 is also divisible by 3. So solve the Euclids division lemma by considering value of b as 3. You get these three corresponding equations. Expand these three equations. Take 9 as a common factor. You will get three corresponding equations: 3 into some constant, 3 into some constant plus 1, 3 into some constant plus 8. We have assigned this value m as this constant, so you got three equations in certain form. So replace 3q cube by m, it will be 9m. It is of the form 9m plus 1, 9m plus 8. That is our required answer. So one more thing in this chapter is to understand that you have applied Euclids division algorithm only for positive integers. If you see in every problem we have assumed that a be any positive integer, so it can be extended for all integers except 0. Okay, that is, we have assumed we have applied Euclids division algorithm for only positive integers. It can be extended for all integers except 0. That is, value of b should not be equal to 0. But we shall not discuss this aspect here. This is mentioned in your book. What does this mean? It can be applied to value of b can be 0 in those equations, but that is not in your syllabus. In your syllabus only the simple conditions that b should be a positive integer, that is there. So if b is equal to 0, then it will be a different problem. Or in your syllabus you have the examples where only value of b is only a positive integer. Okay, that will be all about this exercise 5. That is end of the exercise 1.1 problem 5. Now the problem 5 is little bit lengthy. If you revise this solution, it will be easier for you to understand. I have written it in detail form as far as possible. Only thing is, if you follow these steps, from here we have started again here, and then from here we have written the final answer here. So if you have any suggestions regarding this video, or if you have any doubts, you can always put those doubts in comment section. Please do subscribe the channel. We'll be putting more video lectures on this channel. We'll improve. If you give suggestions, we can improve, because this is our new channel, so there might be some errors, there might be some it might be less video quality, or anything related to concepts, or any other doubts you have, any suggestions, you can put those in comment section, so that we will be able to improve next time. Okay, thank you for watching. Good day.